So my name is Mayank, and I'm part of the FlashArray product management team on the platform side. And what I'm going to do is first, I'm going to introduce two new exciting announcements on the FlashArray product side. But before I do that, I'm going to walk through a bit more on the FlashArray journey. So let's get into it. Right. Since Pure Storage's inception, there's been a focus on getting flash media mainstream into data centers, which have been historically predominated by spinning disk. Right. Through each one of our generations, we've got improvements in density and improvements in performance tracking along the evolvement in both in storage as well as computing side. With these generations of FlashArray, what we've offered to our customers is 7 generations that they can seamlessly upgrade with zero downtime, and at pretty much everything included in their Evergreen subscription. With every upgrade, they've had access to the latest hardware or software features that were enabled on FlashArray. Right? So I think that's been pretty phenomenal. And talking about software innovations, the Purity operating environment is pretty much the heart and soul of FlashArray. And it's had a pretty rich evolution on its roadmap as well. There's been data protection services such as synchronous replications. There have been expansions into cloud integrations that you just heard about with Cloud Block Store. And there has always been pushing the envelope on the performance side with recent announcements such as DirectFlash Fabric that we announced earlier this year. So this year, we celebrate Pure's 10th anniversary. And with that, what we've done is pretty much delivered a 10x better product along those parameters that you see at the back. So I'm going to switch gears and talk about what's up for next. New media types are evolving. And on both sides of the spectrum, right, with OPTANE or storage class memory, we have the opportunity to break barriers on performance end of the spectrum. On the other side of the spectrum, with QLC NAND, we have the option to break economic barriers for our customers with lower cost per gigabyte. With that, I'm going to lead into the first announcement that we have today, which is DirectMemory technology. And this expands read caching functionality on our existing FlashArray X's. Right? And it's going to get about up to 50% performance improvements more on the latency front to our customers. The second key announcement that I have is FlashArray C. So FlashArray C is a new product family that we're introducing in FlashArray. It's a capacity-optimized 100% NVMe offering that will expand all the rich data services that you've seen with FlashArray X. So similar experience now ported over to use cases outside of Tier 1. What you can expect is 6 nines of availability, Pure 1 cloud management, all the API integrations that we have, as well as the predictive support that we've always been proud of. With those two announcements, what it does to our product portfolio is it expands the spectrum, right? On the top, you have SEM expanding use cases onto the performance realm. And at the bottom, FlashArray C can address all the use cases outside of Tier 1, right? And a lot of our customers have been giving us this feedback. And we are very happy to come and enter this space as well. Next up, what you'll hear is a 2-part presentation. So I'll have Steve McQuerry, who will give a deep dive on DirectMemory technology. And then we'll follow up with Pete, who's going to give a deep dive on FlashArray C. So hold your questions on each one of those products until then. Thank you.
Thanks, Mayank. Good afternoon, everyone. My name is Steve McQuerry. I'm a technical marketing engineer on the platform team. And today I'm going to talk to you about DirectMemory, specifically DirectMemory using storage class memory. So kind of as Mayank went through and talked about the history of the product, right, we can kind of step back and take a look at what has happened from a performance standpoint as we've gone through that same history, right? We all know where we came from the legacy disk arrays. And when we started introducing our products, right, we added flash to that. Then when we started adding flash, we started building our own platforms. And of course, we started doing direct flash, right? So within each step of this platform, we innovated somewhere to get some additional throughput, some additional performance. So direct flash allowed us to reduce the latency by 50%, right? In January of this year, we announced Direct Flash Fabric, which is essentially NVMe over Fabric. For us, the initial offering being NVMe Rocky, right? We had already been using NVMe Rocky with the Direct Flash shelf since about this time last year. Well, actually a little sooner than this time last year. But that offered it for the front end. So it starts to give us some options where customers can take advantage of lower latencies connecting to these arrays and starts to open up different use cases, specifically around disaggregation or building out rack scale type of technologies. Of course, there's still the other barrier, is the read barrier, right? How do we increase the read performance a little bit more? So what we're announcing, or what we're doing with DirectMemory, is we're adding storage class memory into the platform as a read cache to give us yet more performance improvements. So now when we start looking at the end-to-end latencies, we can really reduce these down into the 150, 200 microsecond type of latencies. So we're getting to near DAS-like performance on a shared storage array. So it opens up a lot of new opportunities, and it provides a lot of new use cases for where customers may have not looked at this type of technology in the past.
Steve, are you saying those are those read latencies or read and write latencies?
So DirectMemory is going to address read latency specifically. So this is typically a read latency chart that we're talking about here. Okay. Yes, good question.
But you already have like a write cache, right?
Right. NVRAM, the
write cache is already SCM or no?
No. The NVRAM is actually DIMMs, right, Pete? DRAM, yeah. So those are at the top. Much faster. So again, direct memory. This is actually a part of a family. We talk about direct memory.
You're not supporting multiple classes of flash with direct memory, like SCM as well as normal?
Let me get into that. The answer is yes. We'll actually have multiple types of flash in the system, direct memory as well as regular flash. As I go through it, that'll become more evident. If it's not, please come back and make sure that I clarify that. So from a direct memory read caching technology, direct memory cache is actually two different components. We'll talk about SCM and we'll talk about purity optimized. Part of it's hardware, part of it's software. So it's two pillars that actually make up the product. The first of that being a hardware portion, which is storage class memory. So when we look at access to an application and it's actually trying to read information, right? The closer we can get that to the CPU, obviously the better performance. So we go from SRAM cache to DRAM. SCM becomes that middle ground between DRAM and flash. Now there are two different types of storage class memory that Intel offers and other people in the industry offer as well. One is a DIMM that uses the basically DRT interface on the newer platforms, the Intel platforms, that is in the microseconds or seconds or microseconds of latency. The difference or the thing about that is it has to go on the processor board. So you're swapping out DRAM for storage class memory. It's not as fast as DRAM, but it is persistent. So there's some trade-offs there. There's also some things about it has to be 4-to-1 as far as if you're doing a 512K storage class memory, you have to do 128K DRAM. So it's really, it's not complex, it's just not very flexible in the way that you configure it, and it's a little more harder to consume. The other one is the drive, the OPTANE drive. So that's what we've introduced is the NVMe OPTANE drive as a module that plugs into the FlashArray. So what it is a high-speed caching system that reduces latency for high-performance applications, reduces read latency for high-performance applications. So hinged on storage class memory or Intel technology, caching, so it's looking for things that's being repetitively used over and over, right? And again, read latency. We've already got the NVRAM where we're dealing with write, so this brings us into the read. The key to this is the applications that we're targeting are those with high locality, somewhere where the data is read multiple times over some lifetime or some short period of time, so that we're utilizing that. So analytic type of workloads, right? We may expand it into other workloads eventually, but initially it's these high locality type of workloads. And again, high throughput latency sensitive applications. This would be available to anyone, but you would actually look to use it if you were trying to reduce the latency in the application to either get some type of advantage on how quickly you can return the data, how quickly you can get the information back, or shorten the run of an actual job.
So how sophisticated is your mechanism to populate the direct memory read cache? I mean, there's plenty of things you can do with read caching, some of which are sophisticated, some of which are not. I mean, I'm just trying to understand what level of read cache capability are you building into the system?
Okay, can you ask the question again? I missed the very beginning of it.
There are many different types of read caching available in the world today.
Yes.
For instance, sequential prefetch and things of that nature.
Right.
You guys do that?
Not today, right?
And so
we're using an LRU algorithm.
So it's least recently used.
Yep.
Any block that's been, however many fit in whatever amount of direct memory we have.
Yep.
As long as it's being referenced actively enough, it'll stay there.
Correct.
There's
And
no
I can
binding of data to the read cache or anything like that.
I can talk through that a little bit. Say that that last part one more time. Sorry, my hearing's
No
not
binding of data, or
the binding of data, like a LUN specifically to the read cache. No, we don't support that today. No, it's literally looking at the locality of the data and how frequently it's used. So we're not going.
Direct memory module, you're actually replacing an SSD in the
Yes.
FlashArray X.
Yes, we are going to replace an SSD with the direct memory module.
Is it before or after the duplication and compression?
So we've got a little more detail on this, but I'll go ahead and answer it anyway. It's actually going to be after the deduplication, but it's going to be uncompressed. So we're going to have uncompressed data in the cache, but it will still be a block that could be a deduplicated block.
Okay.
So again, we'll talk through some of these details. Hopefully it'll become, I'll get through the glossy slides and we'll get into the real meat of the action here in just a second. So it is a module, slides into a slot in FlashArray. So you are swapping out a direct flash module for a direct memory module. That's one pillar, that's the hardware pillar. The other part of this is the direct memory cache software, which is part of Purity Optimize. Purity Optimize are the two pillars of Purity Optimize that we'll talk about this week, are the direct memory cache software, as well as always on QoS. So in this case, this is the algorithm, right? This is the part that's choosing what data gets put into the direct memory cache.
What did you do before you had direct memory for read caching? Did you use DRAM?
We use DRAM, yes.
Before.
So we do have caching that happens in the system today. It is used in DRAM. Of course, that DRAM is used for a lot of different things, right? And it contains metadata as well as data. So what this is essentially doing is replacing the DRAM for the data portion. So for the data blocks that we were putting in.
Metadata caching being done with SCM.
SCM will be doing the data caching today. Will be, moving forward. If you don't have it, it will still be the DRAM that does it.
I'm sorry.
Did you say not metadata?
Direct memory will not cache metadata.
No, missed that. Thank you. Direct memory will not cache metadata. Metadata will still be cached in memory.
Okay.
That is correct. Cache operation. So this will hopefully explain a little bit of this a little bit better, right? So at the top level, we've got Purity running, right? That's the software. Obviously, we're still doing our writes the way we're always doing, and we are still putting all of the data on the direct flash modules. So the direct flash modules is still the persistent data. It's still the data protection. We're doing dedupe. We're doing encryption. We're doing all of the other data protection, data reduction algorithms on that data. So that's where the data is going to be persistently stored. Any changes will be made there. Basically, what we're doing with the read cache, as I mentioned, we're expanding what cache we have available today, which is in memory, which is very small gigabytes, into terabytes of data that now become read cache. Basically, we're going to have a 3 terabyte and a 6 terabyte configuration. So these direct memory modules will then contain that hot data. So as the data becomes used multiple times, it will be placed into the direct memory. So now that when we do a read, we're going to go to direct memory to do that read. So how that shortens it up, right? Today we would do the read IO, metadata lookup, read from flash, where we would decompress and then return the data. Essentially, we're going to have no need for decompression. And because we're not reading from flash, which is in the hundreds of microseconds, we're reading from SCM, which is in the tens of microseconds, right? So we're able to reduce read service latency end to end on the system from about 200 to 300 microseconds to 100 to 200 microseconds, kind of depending on what's happening.
And does it start pre-staging and pre-loading information it thinks is going to be hot data based upon prior reads of certain things? I've seen it done in Oracle and SQL contexts. And
so when you initially start it up, no. There will be no prefetching, there will be no pre-reads, right? Mm-hmm. It will accumulate hot data as the read process goes on. Now there's no time involved in it. So it's essentially a set of buffers. If it's replaced by something else that's being used more frequently, then something could, we'll call it age out. I hate the word age because the LRU doesn't really use an aging concept.
That was kind of what the timers look like.
Yeah, it's really a set of buffers. So if I've got 6 terabytes and I read a 3 terabyte load in there, and then I don't use it, and then I read another terabyte, I've got the room to do that. And then I go back and start reading that other 3 terabytes again, assuming that nothing's pushed it out, it would still be there. So it's not specifically tied to a timer, it's tied to the buffer space.
But while not being tied to a timer, it doesn't have a timer, so that way stuff that hasn't been read in a while is then stale or not. And that raises the case of, does data become stale at that point? How often does it go and update itself from what's actually sitting on disk at that point?
Right. So if anything that's on
mechanism, it's not a write mechanism.
It's not a write mechanism. If anything on disk changes, that block that's in read cache will no longer be valid for a read of that data. So that particular block would, exactly. So that particular block will age out over time. Eventually there'll be enough data pushed in that it ages out over time. But let's say you're reading something and you read it once and then you don't read it again for a period of time, right? Is that interesting enough for us to put into cache? And by a period of time, I mean, an hour. Probably not, right? If it's in another 2 or 3 seconds, it's going to be interesting. So it's really a set of buffers. Again, there's no time involved, but because there are buffers and how frequently we read, we're going to do essentially a look back period to say, oh, we've read that. That's interesting. We saw it again. Let's put it into cache. Versus, oh, we read that. It goes through the buffer system. It's no longer interesting. We read it again. It doesn't go into cache. So it has to be frequently enough read to be populated, then there has to be enough of that populated to push the older stuff out.
I'd be curious around what the garbage collection and how it's doing that as far as blocks that are sitting on disk. Because over the past several decades, when other people have done similar type of approaches, they had various mechanisms in place for detection of that hot data and how long it's going to stage around and what have you. Aside from the occasionally checking on disk to see if the CRC checksum change, and then we have to reread that information and then pull it off disk.
Yeah.
And
so
the latency flips that you'll experience because while things may look really, really low, then you'll have some spikes that go when it's actually in production.
Yeah, and I think the difference we're talking about is the idea of a tiering technology versus a caching technology. I mean, they're very similar.
Both.
Yes. Yes.
So there's the tiering part, but then there's actually a separate caching component because I've seen what can look like artificial performance problems that aren't actually there because of how it's actually playing the data back.
Yes, I would agree with you. So yeah, so the way the algorithm is working, essentially it's just an LRU algorithm, right? The key of how we populate it is it interesting enough? So we're not prefetching today. We're not going out and looking at anything that tells us specifically this data, because it's been read in the past, needs to go in here. It is a matter of this is the amount of cache we have. We'll fill it up. Once it fills up, we'll start evicting stuff and we'll put new things in. The way it's playing out with the stuff we're testing now, it's working well for specific workloads. There are other workloads that it may not work as well on. As we work with customers on this and we see different workloads, there are things that have already come up, like can I pin a volume to this? These are questions we've had asked by customers, right? So these are things we'll continue to investigate, as well as do we want to prefetch some data. Right now, those are the types of things that I think we'll continue to kind of see what's happening and see how this evolves. Pete, would you have anything to add to that?
We can already tell that the algorithm we've selected actually was derived from analyzing customer data. So we can tell it'll have a wide applicability to a lot of customers. And in pure style, it won't be the best thing for a small subset, but it'll kind of hit the sweet spot. And like Steve said, it'll evolve. We'll take feedback from arrays and from customers on how to kind of evolve it.
So one question, that first stack there, is that a read hit or a read miss?
That would be a read miss, and that would still be a read miss.
Actually look like?
A read hit would be the write. A read hit on cache would be the stack on the right.
Without direct memory, what is a read hit?
A read hit in
current flash array.
In DRAM?
Yes.
Pete, I don't have that information. Do you know that? What's a read hit in RAM? Service latency. So if we have a read hit in RAM, it's going to be obviously less than 100 microseconds.
So yeah, I think the concept today is there's a cache that exists. It's not even worth talking about.
It's too small.
It's trivial. So I would actually challenge you to even craft a benchmark to tell. I've seen it.
I'm sure we can craft a benchmark that would access the same block 5,000 times.
Yep.
Like that, yeah.
And so if that's all you do, you'll see it. If you access a couple other blocks, you'll probably blur it out. It's trivial.
If you had a really tiny data set, really, really small when you read it over and over, yeah. I mean, but it's like Pete says, it's not going to be a real world application. It'd be a benchmark.
So I guess that bleeds into the next level of use case. So I'm from kind of the ERP space where we're looking at in-memory databases, et cetera, and looking to extend in-memory databases and DRAM to storage class memory, and where those advantages are there and where the vendors are working with Intel to optimize those applications to better perform because of these exact challenges. When they're expanding the idea to an entire storage array with mixed workloads, do you guys have numbers on kind of what the hit ratio is for this expanded level of storage class memory in the storage array?
Okay.
Because I can clearly see the advantages for direct attack storage. I'm not as readily seeing the advantages for if I have, 100 different workloads spread across hitting a storage array and how that would help my overall performance in a data center.
Okay. I'm going to skip this slide for just a second because your question is actually going to be the next slide, and then we'll come back to this one. This is fairly evident. So this is an analysis of pure metadata of our customer base, right? Looking at our customer base today, we started tracking data locality, basically how frequently data is read in a particular area on our systems, on our customer systems with like 4.1.10, I believe, somewhere in that time frame. So we're able to take that information and see if we were to put cache in a system, and these are mixed workloads, right? This is not a specific workload. We really have no idea because we've actually had this discussion is how can we tell on a customer array what workload would benefit from this? We basically have to kind of figure it out as they go along right now. We're working on things that will model that better. But 80% of our arrays that are out there in our fleet, and this is not an analysis of all of them, this is the higher end, because we expect customers with higher end arrays to care about this. If you've got an X10 or an X20, you probably don't care about performance. 80% of the arrays could get 20% lower latency, whereas 40 of them could get 30 to 50% lower latency based on the workloads they're running today. We're going to have a tool. If you've got an existing array, we can model this for you. We are going to have tools that will allow this to be done within Pure One, where we can model this type of data for customers as well. So this is one of the things that's really nice is, again, based on the algorithm, the things we've done, this is what we expect our customers to see. We've got a couple of betas. One of our customers had pretty high locality on their beta. They were getting about a 30% cache hit in some instances, not for long periods of time, with the data that they had on there. They went to 90%, and it reduced their latency by about 50 to 60 milliseconds on the read service, right, which is kind of what would be expected. So to answer your question, yeah, we actually have a way of looking at this.
Now, can you tell it to not cache certain volumes?
No, we don't have that ability yet.
You don't have that ability today?
No. Straight, if it's hitting the algorithm and it's being read frequently, it's going in. Is that something we could look to add in the future? Absolutely. This will come. A lot of this will come on use cases and customer feedback.
So to Keith's comment there is, I can't pin my SAP HANA today, but I want to. But I also happen to be running Exchange and a bunch of other applications on a particular array. I want to try to prioritize that more, but the answer is no, not today.
Theoretically, though, I can see where if your SAP HANA data set resides on a flash array, and your whatever other workload that is intensive for read cache elements sits on a different flash array, even if they're clustered, and you have this storage class memory sitting in both of these arrays, you could theoretically pin it because this cache will cache the HANA database, and that'll cache the Cassandra database.
I heard you say buy an array for each application.
That's what I'm saying.
But
I'm a salesman.
It's called right sizing.
You laugh at that, but
No,
in SAP world, that's what we do. We buy an array for SAP because we can't solve this problem. So it's either direct attack storage, or we buy an array for SAP HANA
But direct
so that we
attack
won't have
storage
this problem.
doesn't solve this problem either.
Direct attack storage, in theory, storage class memory, if I can get the density that I need, it's when I surpass the density that I need that I start to look at.
Yeah, so I kind of ignored that part of the question, but since you brought it back up, I will. I won't ignore it. We've talked to Intel when we started talking to them about some of this stuff. They were interested in some of the workloads we've run with SAP. So our solutions team did a lot of testing with SAP, but not specifically with this as the in-storage memory for the compute node, right? This becomes a tier. And I think we've got some stuff on that this week that we're going to talk about. So it's really interesting, the economics they've done. The storage class memory in the server itself becomes a very, very interesting use case, and it's much faster, right? But it's not the same necessarily speed and cost of what's happening in the server itself if it's DRAM, but there's still some obstacles to overcome, such as what's the data protection mechanism? What happens when that fails? How do you get it out? There's a lot of serviceability things that they haven't figured out yet.
Practical problems. Like
exactly.
I can have a race car if I want inside, but I need to replicate data off-site. And SAP isn't the best mechanism for me to replicate my data.
Yeah.
That software mechanism is not good enough. I need storage class replication to solve my data protection problems and my snapshot problems and all of that. SAP hasn't solved that. So there's definitely a piece to this. I'd also like to know what type of other HPC type of workloads benefit from the trade-off of not having the data local inside the storage array, but also having the advantages of a storage array.
I would say a particularly viable model of that is high-frequency trading.
Yeah.
That biomedical engineering, HPC under petrochemical or seismic elements.
Yeah, because if I can get to a point where I can abstract my compute away from that storage class memory and get some of the same benefits, a little bit lower latency, a little bit higher latency, but I can attach different workloads to, I can use the SAN for what it's for, then I can see some advantages.
Yeah, and I think what we're trying to address is that middle ground, right? Let's give you some read latency performance to kind of address that direct attached storage market where you have the benefits of the storage array as well, right? And that's kind of the model that we've been doing with NVMe over Fabric as well as DirectMemory. We'll evolve this, clearly. It's an introductory product from a storage class memory offering, so it'll be interesting to kind of see where this goes. So when we talk about these numbers down at the bottom here, I kind of skipped over the slide that explains this. This is the lower latency achieved. To get 50% lower latency, you have to have 100% hit rate, right? So we see what is the expected hit rate of the fleet. Expected 100% hit rate is not really high. I was going to put a slide in here that said 60% of the time it works all the time. It works every time.
Yeah, that would be awesome.
Then I was like, then it's going to be out there.
Yeah. We should have as much cache as we have disk space in the array.
Great idea. In fact, why don't we?
Sure.
I've had that before in the past.
Yeah. From a real numbers perspective, right? This is our read service latency. This is with 100% hit rate. This is pretty consistently 50% all the way across the board. So really, as the IOPS go up, it doesn't really change. The scale over there, that's like 240, 240 and 480 or something like that. It's not even 480, it's like 300 something. Those are a little bit higher just because of the size of the blocks, but still consistent. Doesn't matter what block size we throw at it. If the hit rate is consistent, it's linear, right? If you're at 100% hit rate, you're at 50%. If you're at a 50% hit rate, you're at 25%. It's purely linear from a scale perspective.
The chart should look the same if this were 64K or higher.
Yes, it does.
Just that since it doesn't show 64K, I have to ask.
Yeah, no, it does. And if it's 128, I mean, we've got it all. We just picked 4 and 32. Okay. Yeah, but it is, the numbers change clearly from a read service latency because the read service latency is going to be higher on a higher block size, right? But as far as the percentage and the hit rate, it's consistent across all block sizes.
And this is all free?
I love that.
I don't know.
Oh, wait, you didn't tell me it was free. Huh.
Talk to your account representative. I work in platform. I don't do pricing. I have no idea. I actually don't know what this stuff costs, to be honest with you. I don't want to know for the most part. So direct memory modules insert into the flash array, right? So these are PCIe connected devices inserting into the flash array. They go into the modules that we have on the shelf today. You know, this is kind of, again, a testament to when we build our own platforms and we build our own products, we start having options. So this is the first offering of something we plugged into a flash array that is not a direct flash module. Now, it's still very similar, right? But it is a different purpose and serves a different purpose from the purity perspective as well. As I mentioned before, two different sizings. An 878, I'm sorry. Wow, wrong world. That's you. A 3 terabyte or a 6 terabyte, 4 by 750. Those are the offerings today. Long term, and we kind of danced around this, or not long term, I guess to kind of wrap it all up, we kind of danced around this in a lot of the conversations we've been having about those type of applications. It's where do we see things going from a high performance application standpoint? You know, we've seen this real transition to DAS for a couple of reasons. Economies of scale, right? Having the type of storage, platform's not the right word, but the type of storage software out there that can give us the redundancy and the type of services we want to see, as well as, you know, the types of performance. That world shifts back and forth from time to time. The nice thing about, you know, shared storage is it is shared storage. You get the economies of scale, you get the data reduction, you get a lot of the benefits, but you start compromising on performance. So you have to find that balance. What we're trying to do is bring back some of that compromise from performance. So how can we start to see direct attached storage applications run with a storage array, with shared storage? So that's the model I mentioned earlier. I talked about disaggregation, whether you want to call it disaggregation or you want to call it rack scale or rack deployment. We've got customers who are starting to do this, right? They've looked at where they've had, you know, just straight NVMe devices in servers in a rack, and they're with NVMe over Fabric. They're like, we can get the same type of efficiencies, or we can get the same type of performance or near that performance with better efficiencies and better management. Now, when we start to increase the read latency even more, decrease the read latency even more. Yeah, we don't want to increase it, sorry. Decrease the read latency anymore and increase the performance. We've got yet another way that we can look at starting to change these applications.
Yeah, and also adding in the elements of benefit of a consolidated storage array.
Exactly, yeah, with having those benefits. Thank you. You completed my thought. I didn't actually say that. Thank you so much.